Okay, this is the next section in section 3.5, implicit differentiation. And what you want to know first is the difference between an implicit equation and an explicit equation or function. An implicit is what you're used to, or I'm sorry, an explicit. An explicit is what you're used to, something like y equals x squared minus x plus 2. Even x to the 12th, right? Minus x plus 2. Anything that is written as one variable in terms of another variable, that's explicit. An implicit equation would have them mixed together. First, let me give you an example of an implicit equation that we would be able to deal with. Deal with meaning like in an old way. So if we had xy equals 4, that's implicit because it's written in terms of x and y together equals something else. This could have been 4 plus x. But if we wanted to get the y by itself, we could by dividing both sides by x. Let's add some more things to that, or let's do a different one. Maybe we had xy minus 4x plus 2y equals y squared. In this equation, you can't solve for one variable in terms of the other. Either it would be very bad or it's just completely impossible. So in either case, that's when you want a way to find derivatives of functions like this without having to solve for one variable, because again, sometimes it's impossible, and that's going to be called implicit differentiation. Before we do an implicit differentiation problem, let's see how to differentiate some different terms with respect to x. The first one should be very familiar, the derivative with respect to x of x cubed. Now what you want to notice here is it says the variables agree. So you know the derivative of x cubed, right? Hopefully you're writing it before I am. 3x squared. Now, one thing that you don't realize that you're putting there, and I'm going to actually do it, is that we're differentiating an x term with respect to x. So since the variables agree, and if I want to think about the chain rule, what I'm really also multiplying by here is the derivative of the variable with respect to that variable. Okay, the derivative of x with respect to x, the derivative of x with respect to x. Now again, since these are the same, dx over dx equals 1, so we don't write it. Okay, we don't write this. We don't even think about it. We just write 3x squared. But when we get the derivative of a y term, and we are differentiating with respect to x, here I'm differentiating y cubed with respect to x, well now I'm going to need that extra part. So this is going to be 3y squared, because I'm using my normal rules, now times the derivative of y with respect to x. Okay, times the derivative of y with respect to x. So here I do need that extra term. Alright, and let's make sure that you know what you're doing, and do it one more time. Down here we want the derivative of x plus 3y with respect to x. So when we take our derivative of x with respect to x, we don't need to write that extra term. But when we take a derivative of y, a y term with respect to x, we do need that extra term. So the derivative of x, it's actually a 1x, so the derivative is 1, plus the derivative of 3y would be 3, but it was a derivative of a y term with respect to x, so we needed that extra term. Alright, let's try one more term that has x's and y's. Now, notice that this is a product. This is the product of x times y squared. So to find the derivative of xy squared, we need a product rule. So I'm going to write derivative of the first times, I'll do them in colors, times the second, plus the derivative of the second, which would be 2y dy dx, because it's a derivative of a y term with respect to x, derivative of the second times the first. And then you just make it look a little bit neater. 1 times y squared. And why don't I put these together and put them in alphabetical order. So plus 2xy dy dx. So that's differentiating with respect to, that's differentiating an implicit expression where the x's and y's are mixed together. In general, here are your guidelines to differentiate implicitly. I would just leave it to you to pause the video, write these steps down in your notes, and we're going to do an example in the next couple slides. Okay, for this one example, you'll notice that the steps are written out, so obviously normally this is not going to be the case. So in the first one it says differentiate both sides of the equation with respect to x. So I have rewritten the equation up here. This is implicit because it has a mix of y terms and x terms in the same equation. So you would know that you had to use implicit differentiation. Alright, so to differentiate each term with respect to x, we want to take first the derivative of y cubed with respect to x, and then this, and so on, all the way across. Okay, so the derivative of y cubed with respect to x is 3y squared dy dx. Next we have a 2y dy dx. Next we have a 5 dy dx. Next we have just a 2x. We don't need to write dx dx. And the derivative of negative 4, since that's a constant, is 0. Okay, now on the next page, I'm going to need to remember what I just wrote. Okay, 3y squared minus 2y minus 5. Okay, so you see that our first step now is to collect the dy dx terms on the left side. If you have your notes in front of you and you were writing it down so far, you see they're already on the left. So I will just rewrite them. 3y squared dy dx plus 2y dy dx minus 5 dy dx. But since I am collecting those on the left side, I want to leave everything else on the right side, or put it there. So I'm going to move my minus x squared to the other side, and then there was a 0, so there's nothing else on that side. Alright, next step. I'm going to factor a dy dx out of the left side since all of these terms have one. So dy dx factored out leaves you with 3y squared plus 2y minus 5, and that equals x squared. And the last step, you can solve for isolate the dy dx by dividing by that trinomial, because then it would cancel over there. So your last step is that dy dx equals x squared over 3y squared plus 2y minus 5. Alright, now what does this mean? So far we've found our derivative. What it means is illustrated on the next page. Now, the original equation, which is down here, y cubed plus y squared minus 5y minus x squared equals negative 4, that equation can be graphed. There is a mode in your calculator called parametric mode where you can graph equations that are not functions. And you know this isn't a function because it doesn't pass the vertical line test, but you would still be able to graph this. Now this is the graph of this equation, and they've just picked some points that are on the graph, plug them into the derivative that you just found, and if you plug the point 20 in, you get a negative 4/5 from your derivative. And you can see that makes sense. It looks like it's about a negative 1, but not quite. If you would plug in a 1, 1 to that equation, you would get undefined. If you plug in a 0, negative 3, you would get undefined. If you plug in 0 for x, no matter what the denominator was, no matter what the y value is, you would get 0 for your slope and so on. So just to recap, this implicit equation, because it's implicit because it has x's and y's mixed together, has this for its derivative. And from the graph, again, all the things we went over on the last slide, are just reiterated here. And in the next video, you'll have one more use for implicit differentiation.